Okay, here we go. Writing on the board killed too much time erasing to make it large enough, so here's an attempt of writing on multiple pieces of paper. What I'd like to do is review a little bit from section 4 in the text and looking at the family of functions mu times x. Times 1 minus x. And then investigate what some of those properties are. So it may be helpful to write it as mu x minus mu x squared. For example, if we wanted to find the derivative, then that would be mu minus 2 mu x. That can be helpful for some computations that we're going to be doing. Another thing we may be interested in is looking for a fixed point. And a fixed point would be where the function is equal to the input value, so that the input value equals the output value. And so we can solve that by bringing everything over on one side. And you have mu x squared minus mu x plus x. And you could factor out an x, and you have mu x minus mu minus 1, if you like. And so for that to equal 0, you get either x equals 0, which is maybe the obvious case anyway, and then you get this guy equals 0. So mu x minus mu minus 1 equals 0, which then gives you that mu x equals mu minus 1, or x is the mu minus 1 over mu that they mention in the text. And so what they call this is P sub mu as the point that is a fixed point that depends on that value mu. So what that means is that we found something about the dynamical behavior of two fixed points for every member of this family of functions. Mu equals 0 wouldn't really work very well here, but mu equals 0 would be a real boring function. That would be the function that's constant 0, so who cares? So this gives us a characterization of the fixed points for everybody in that family. Now, it may be interesting for us to try to determine what those fixed points do in terms of attractors and repellers. But first I'd like to step aside and do a little more of the geometrical stuff. I mean, after all, this function for any of those values of mu is a parabola. And we get that the intersections with the x-axis are x equals 0 and x equals 1. So every member of the family is going to go through here, it's going to go through there, and it's going to come up in various ways. It may come up very shallow and do something like that. It may come up very steeply and have a peak in here someplace. It may do something in between and be exactly tangent right there at the origin. Come on through and then come back down. It could get real crazy and go up really steeply and go outside the box if the mu were big enough. And so all those are reasonable members of the family where it's probably pretty clear that the behaviors are going to be very different. And so one thing that we could do, even without referring to our dynamical behavior of hyperbolic and non-hyperbolic fixed points and stuff, is to try to talk about the members of the family and how their behaviors depend on what that value of mu is. For example, the really shallow one that came across here first had a fixed point there, and if we extended this line on down, pinch that up a little bit, this shallow parabola is going to eventually curve down and have the other fixed point happen way down there someplace. Right? And so that's not the kind that we're going to worry about. We don't want to play with those very much. The one that came in and was exactly tangent right there, despite my amazing artwork, so that the reference line and the curve, they were tangent right there, then that one's interesting because it looks like for these tall guys, there's a fixed point there and there, there's a fixed point there at the origin, and as you make them a little bit shallower, comes across like that, then there's one there. It's sort of like as you make them shallower, this fixed point is creeping down the reference line until it looks like that's the value where maybe both fixed points are the same fixed point, and there's a unique fixed point. And then will be the other members of the family about whom we don't really care where it fits down there someplace. And then ultimately, if you want to really get crazy about this, then if the mu on the front were negative, then the whole family would turn around and it'd be a parabola that had the same two intercepts of the x-axis, but it would open that way, which makes for a really different kind of intersection with our reference line, and so we don't really want to deal with those either. So some of the questions we could ask were where some of those various behaviors happen. So from the function having the derivative of f prime was mu minus 2 mu x. Oops, there we go. If we wanted to know what the value of the derivative is at the origin, then you obviously just plug in 0 and you just get mu. And so it's a pretty quick answer that mu equals 1 is the case where you have exactly that tangency thing we were talking about. Comes up, it's tangent exactly right there, bumps across, and only has that one fixed point instead of two different fixed points. And so that it looks like for mu bigger than 1 is exactly when it's going to be going a little bit higher, and so it's going to have the fixed point there and then another one up there someplace. So that's going to exactly be the breakdown if we're going to one fixed point to two fixed points. Well, okay, fine. So what is that fixed point? We found it. It was the mu minus 1 over mu, right? And so we can even then do our hyperbolic test. And so if we take, again, that derivative, is mu minus 2 mu x, and we plugged in the 0. Now, not in the sense of testing for the geometry of the tangency, but now in the sense of, oh yeah, that's one of our fixed points, and we want to test whether it's hyperbolic or not. Then you put in the mu, and so what you get is a range of values of mu for which the 0 would actually be attracting or repelling. Mu equals 1 is non-hyperbolic, so that's going to be interesting. Mu bigger than 1 means that this derivative, that 0 is bigger than 1, which means 0 is a repeller. So then what about the other guy? Well, if we plug in the mu minus 1 over mu, the other fixed point guy, into the derivative, then what we get is mu minus 2 mu times that value. The mu's cancels, not as bad as it might be. Mu minus 2 mu plus 2, which gives you 2 minus mu. So for the member of the family that has mu as the parameter in the front, then this fixed point, which is mu minus 1 over mu, is going to be hyperbolic or non-hyperbolic, attracting or repelling, depending on the behavior of that value that we just found right there. So the switchover places are going to be where 2 minus mu is equal to 1, which means mu equals 1 and mu equals 3. And for values in between there, what we have is that if mu is between 1 and 3, then that derivative evaluated at that second fixed point, the non-trivial fixed point, is going to be, well, you plug in a number in there, right? You get that that's less than 1. So it's an attractor. So what you get is exactly on this interval, and that's where we're going to focus our attention for a while here. We could completely characterize the behavior of what goes on, and that is that 0 is a repeller, and the other guy, p sub mu, which is the mu minus 1 over mu, is an attractor. And that's totally consistent with the way that we've been drawing these pictures. And that is, what are mu's between 1 and 3 going to behave like? Well, if you think about it, that mu equals 3 was giving us mu equals 3 is going to give you that the derivative at the fixed point is exactly minus 1. So that means we can actually sketch the graph for that one. We could have, there's the 0 fixed point. So the curve comes up and comes back down just so that when it crosses right there, it looks like the slope is minus 1. That's going to be the value of p sub mu for when mu equals 3. It's exactly got a minus 1 slope. You figure, well, gee, is that when it goes down in here somewhere, up in there someplace? So the one thing that we could investigate that we didn't is some specific values of the geometry of the members of this family. So for example, we found out the one where you've got the tangent, see, at the origin, right there. That was mu equals 1. Now it might be interesting to know, just in the overall land of things, is exactly when it comes up from that fixed point and it peaks right there and goes back down. So all these parabolas are going to have an axis of symmetry, rats, right there, at x equals a half. But the question is, when is x equals a half also going to be the fixed point? And it's pretty easy to verify that that's going to happen when mu equals 2, because you get the function is 2x 1 minus x. And to find out what happens at a half, well, gee, you plug it in. So you get 2 times a half equals a half. Ka-ching, that's a fixed point. So mu equals 2 is the one where that peaks right there, which is interesting. That means up to that point, the secondary crossing, the crossing of the secondary fixed point was happening with a positive slope. This is a place where it has a 0 slope, which you could verify back in that derivative formula. So that means beyond there, the slope starts getting negative, which is kind of what we drew for the 3 case, the mu equals 3 case. But that was just grabbing at the 3 case. Let's see, I guess the other constraint might very well be, what is the case when you've got the fixed point, the vertex is exactly nicking its head on the top of the box and coming back down, so that the other fixed point, gee, off the top of my head, that looks steeper than it did for 3, but who knows? Well, you can verify relatively easily that mu equals 4 is exactly where that happens, because if you have 4x 1 minus x and you plug in a half, you get 4 times a half times a half, which is exactly 1, which means the y value when you plug in a half is exactly come up there and bump your head on the ceiling. So that means we can characterize the family in some sense from the geometry and in some sense from the dynamics, because if mu is between 1 and 3, then we've got the 2 fixed points, and the 0 one is repelling, and the one up in the air somewhere is attracting, up until you get to exactly 3. Between 3 and 4, so here's a prototype of one of those, where you come down, but it's not too steep. So there you're coming down, but you're not coming down with that slope 1 yet, so that would be mu in that range. And that's sort of interesting. If we had between 3 and 4 for mu, then that's going to be a place where you're not bumping your head on the top yet, but by the time you come down, you're already pretty steep, and that's a bad parabola. But still, you can see that slope is more negative than -1. And then after another couple of minutes, there's the other category that if you have the mu actually greater than 4, it comes up and actually goes outside the box, and we're going to investigate that one a little bit more to explore what happens in that case. Now, in this case of the mu between 3 and 4, we had this, the mu between 1 and 3 characterized pretty well, right? You can, the 0 is repelling, curve, line, curve, line, curve, line, curve. You go in. If you started over here, curve, line kicks you over to do what the other guys had done. So you go in there. So that's certainly repelling, and that's certainly attracting, just like we thought, right? Something different happens here. Of course, you could always just hit the right point and hit the fixed point, but what if you miss the fixed point by just a tad? You go vertically to the curve, line, curve, line, curve, line, curve, line, curve, line, curve, line, curve. Oh man, all kinds of weird stuff is happening. That's really why they call it cobwebbing. And that makes sense, because if you plug in a mu bigger than 3, then that derivative thing that we tested, f prime with a mu, with the fixed point p sub mu plugged in, actually an absolute value ends up being bigger than 1, which means it's a repeller. But what's interesting, to me at least, is that that doesn't change the fact that the zero fixed point was also a repeller. Ooh. So if that's a repeller and that's a repeller, and there aren't any other fixed points, then that's one of the very first arguments that we can make, that there's something else interesting dynamically happening in here someplace. Because if that pushes orbits away, that pushes orbits away, then they got to go someplace. Either they go to some other periodic orbit of a period higher than 1, or they dance around, or maybe both. And that's going to be one of the stories that we get to a couple of sections from now. So stay tuned for what happens with this category. This category we already pretty much have under control just from that simple analysis that we did. The book goes through some proof of the attracting, repelling stuff, but it actually fits into our definition that we've had before, so it works. The case that we're going to deal with right now is going to be this mu greater than 4. So here, for reference, let me extend the reference line. Let me extend the axes a little bit. That's the origin. That's 1. And let me extend the parabola a little bit too. The parabola is a big, long fellow, right? And so what happens in the case where mu is actually bigger than 4 is that part of the parabola bumps outside this box of where we felt like everything was happening before. So for example, if you're somewhere here in the middle and you go vertically to the curve, horizontally to the line, vertically to the curve, uh-oh, you're out here, where now you go to the reference line. Yeah, forgot to draw the reference line. The reference line is there, the curve is down there. You go toward minus infinity really pretty quickly. So there's this whole little interval of folks in here that anybody in there as an x as a starting value is going to go, f of x is going to be greater than 1. And if f of x is greater than 1, then, well, even I can do that, right? If it's mu times x times 1 minus x, if f of x is greater than 1, then the next time you plug somebody into there, you're going to get a negative number. And that's what the cobwebbing graph tells you, that that's where the next y value is going to be negative. So that's going to be some interesting case where maybe some folks escape and maybe some folks bounce around inside the box forever. And that's exactly what we're going to be investigating in section 5 as it plays out. So let me take a little break here and see how this looks.